Take a deep breath. Notice how you pulled that air into your lungs? Actually, you didn't. You didn't suck that air in at all. The heavy physical forces of the room around you pushed it inside. We tend to think of the air around us as empty space, but zoom in far enough, and that empty space reveals itself as a dense swarm of billions of physical particles, constantly vibrating and colliding. In the 17th century, a scientist named Robert Boyle realized that if we wanted to understand the physical world, we had to figure out exactly how this invisible substance behaves. His challenge was entirely practical. How do you measure the strength of something you can't even see? And more importantly, how do you predict and control it? To harness the power of the air, Boyle had to find the mathematical rule, hiding in the chaos, a clear mechanical link between physical space and physical force. Look at gas particles trapped in a closed box, randomly ricocheting off sides. Each strike against the wall exerts a tiny force. This collective impact is pressure. Now watch what happens if we crush the box to half its size. The particles haven't changed, but they have significantly less distance to travel. Because the space is halved, they collide with the boundaries twice as often, creating a massive spike in pressure. Shrink the volume, and you force more microscopic impacts. Less space equals higher pressure. That simple box experiment gives us the exact formula for Boyle's law. P1V1 equals P2V2. It works like a physics seesaw, where pressure and volume balance perfectly against each other. They share a precise inverse relationship. This graph shows exactly how that behaves. Plotting pressure on one axis against volume on the other forms a smooth hyperbola curve. As volume decreases, pressure aggressively climbs to maintain the balance. If you take a 4-liter balloon sitting at 1 atmosphere of pressure and compress it down to 2 liters, you have the volume. Following the math, the pressure doubles to 2 atmospheres. This calculation assumes an isothermal environment, meaning the temperature stays exactly the same, and no extra gas is added or lost from the system. By proving that gas acts predictably, this mathematical mirror allows us to manipulate immense physical forces simply by altering the geometry of a container. Because gas responds so reliably to changes in volume, engineers apply this exact equation to build tools we rely on every day. When you push down on the handle of a standard bicycle pump, you aggressively compress the volume of the cylinder. That forces high-pressure air through the valve and into the tire. A medical syringe runs the identical math in reverse. Pulling the plunger back expands the internal volume, which drops the pressure inside the tube. The higher pressure fluid outside then rushes in to fill the void. This logic scales to extreme environments, too. When humans go deep underwater, Boyle's law dictates the terms of survival. The immense weight of the ocean above dramatically increases the ambient pressure, which brutally compresses the volume of the air inside the diver's lungs and their pressurized equipment. The equation P1V1 equals P2V2 is the operational logic that drives our machinery and allows us to function in hostile conditions, which brings us right back to where we started, your own breath. When you inhale, your diaphragm contracts downward. Your lungs physically expand, increasing their internal volume. As volume goes up, internal pressure drops. This creates a low-pressure void inside your chest. The heavier atmospheric air simply pushes down your windpipe to fill that empty space. You don't breathe by pulling air in. You breathe by expanding a box and letting the weight of the sky do the rest. Boyle's law is the invisible mechanical tether that links the microscopic physics of gas to our very ability to stay alive.